These are examples for our reasons for proof. These are not the actual definitions or theorems. These are just examples of how we would use these reasons on a proof. Our first one, using the segment addition postulate. If we have 3 points that are collinear and point B is between points A and C, then using the segment addition postulate, we could say the length of AB plus the length of BC is equal to the length of segment AC. Next, using the reflexive, we can make a statement such as AB equals AB, or measure of angle 1 equals measure of angle 1. And it doesn't seem like that reason is very significant. However, we'll see when it is significant when we use it for subtraction or for proving triangles congruent. Next up, transitive. If we have that CD is equal to EF and segment EF is equal to segment GH, then using the transitive CD equals EF, EF equals GH, we can conclude that CD is equal to GH. Another way that we see this one used sometimes is with expressions or sums. For example, if we have AB plus CD equals EF plus GH, and we also have EF plus GH is equal to JK, then using the transitive property, we see that AB plus CD is equal to this. Here is that exact same expression again, EF plus GH equal to JK. So we can string these together and we can conclude that AB plus CD is equal to JK. So it's another example of how we could use a transitive. One other way that we see the transitive used is if we're stringing more things together. So if angle 1 equals angle 2 equals angle 3 equals angle 4, then we can travel through these equal signs, 1 equals 2, 2 equals 3, 3 equals 4, to conclude then that measure of angle 1 is equal to the measure of angle 4. Next one we have is a definition of midpoint. So if we're told that B is the midpoint of segment AC, that means then that point B must be between points A and C, so we could get the drawing out of that as well. And BA is equal to BC. It doesn't say that either of these segments is half as long as the initial, it just says that these two segments, BA and BC, are equal to each other. And more with this one, since it's a definition, it's actually a biconditional. If we have this drawing and we have that information, then we could say that B is the midpoint of segment AC, so it can work both ways. Next, angle addition postulate. So we're going to put points A, B, C, and D on here. We'll call this angle 1 and call that angle 2. So looking at this, we have angle 1 and angle 2, which together make up this bigger angle. So we can say that the measure of angle 1 plus the measure of angle 2 equals the measure of angle ADC. Next one, definition of angle bisector. So if we know that we have a drawing like this, let's put a few more letters in there, and if we're told that AB is the angle bisector of angle CAD, then we could say, using this definition of angle bisector, that the measure of angle 1 is equal to the measure of angle 2. And if angle 1 equals angle 2, and we have this drawing to go with it, then we could say that AB is the angle bisector of angle CAD, so it's a biconditional again because it's a definition. Next, linear pair postulate. Linear means line, pair means two. So if we have a drawing like this, let's go ahead and use angles 3 and 4 now. Together, 3 and 4 are adjacent angles together that form a line. They are in linear pair. We could say then that angle 3 and angle 4 are supplementary to each other using the linear pair postulate. Now let's go a little bit further with this. This is the definition of supplementary angles. So if you know that angles 3 and 4 are supplementary to each other, when you hear supplementary, you should think of a certain number. You should think of 180 degrees. This means that the measure of 3 plus the measure of 4 must add up to 180 degrees. Again, it's another definition. So since these two angles add up to 180 degrees, we could then say, go in the other direction, that 3 and 4 are supplementary to each other. This one works both ways. Oops. Next one, vertical angle theorem. So we're going to have two lines that intersect with each other. When those two lines intersect, we have angles that are formed. We'll call this one angle 5 and angle 6. 5 and 6 are vertical to each other. And the vertical angle theorem tells us that the measure of 5 is equal to the measure of 6. It's not the definition, but it's the vertical angle theorem that says that they're actually equal to each other.